Thank you. So today I will continue this parallelism between integrable systems and algebraic geometry, and the idea is to review the theory of spaces of initial conditions, first by Okamoto and then by Sakai, and I will try to say the difficulties to do the same in higher dimension. So the story starts with Painlevé. Actually, and I should also quote Gambier, which was a student of him, and he completed the classification of given by Painlevé. And the goal was to define new functions via differential via ODEs, meaning that as a solution of some particular ODE. But to do this in great generality is quite impossible, and I will explain in a second why. So the problem was to find a suitable collection of ODEs for which one can do such analysis. So let me explain what do I mean by difficulties. So the first problem is that in general solutions of ODE are not single value. So this is not really a big deal because this is solved via branched cover. So we know that even if around a point a solution is not single valued, then one can consider a branched cover from some quasi-projective surface to C to C. So a quasi-projective Riemann surface to C. So branched cover, of course, branched along the singularities of the solution, such that the list of the solution to S is single value. So I will give an example in a second because I want to say that the problem is not just this. The problem is that you would like to have some S that works for every solution. So given a solution, you can build an S. But in general, for each solution, you have to build such a branched cover. So the example, so the problem is movable singularities, but I'm going to give an example so that I also clarify what's written here. So movable singularities. Just with an example, if you look at the following differential equation, I hope there is no coefficient, sorry, because we deliver this. Yes, this one. Then if you look at the solutions to this equation, every solution is of the same form, so WT. And I take the occasion to explain the notation. I will never write W of T, but W every time depends on T. So it's 1 over the square root of 2 times T minus C. And all solutions are found by choosing some C inside the complex numbers. So as you can see, the singularities of this function, let me write WC, depends on C. So if I want an association of the E to branched covers, sending a differential equation to a branched cover, this is in general not possible if there are movable singularities around which the solution is not single valued. So this is the prototypical example in which it's not possible. And this is precisely, in a second I'm going to write to the blackboard, the collection of a differential equation chosen by Painlevé is the collection of equations satisfy Painlevé property, which is precisely being single valued around movable singularities. But let me write at the blackboard, so I will be a bit imprecise. I will say theorem, but there will not be statement here. I will just explain the work by them. So this is by Painlevé. So they classified ODEs of the form W second equal to R of W prime E, such that R is rational in W and W prime and homomorphic in T, and every solution is single valid around movable singularities. This is the Painlevé property. Okay, I've written classified up to what? Up to Möbius transformations in all the dependent, time dependent and independent variables. So modulo minus. And in all variables, so in all variables. So, and they showed that there are just 6 isomorphic classes, so it's equivalence classes. So there are 6 equivalence classes, which are denoted by P1, P6, in honor of Painlevé, but actually the 6th one was found by his student Gambier, and that's why Gambier is also mentioned in the result. So, this is very classical and very well known and understood, but all the analysis made by this guy was really analytic. So, it was analysis made by local expansions, so it was very, very involved. The point is that there is this solution, this alternative by Okamoto to classify Painlevé equations, which is called the geometric approach to Painlevé equations, and it is given in terms of these spaces of initial conditions, which is the analog of what I told you last time. Of course, in this setting, I have to build them again, and in order to understand such a differential equation to which of the classes belong, it is enough to look at the geometry of this space of initial conditions. So this we will see this during the seminar. Any question? So now Okamoto space of initial conditions. This is in the 70s. Okay, so now I'm going to build a very long construction, and at the end we will have the space of initial conditions. So the first thing we do is to discard the singularities that we can discard, which are the fixed singularities. We can just forget about them, because we know that they are present for every solution. So the first thing is you define, so for every, I'm fixing some bullet inside the set 1, 6, because it's the same construction for all the equations, actually for every differential equation of this kind. And so then what you do is you define tau to be the C minus fixed singularity. Oh, no. Fixed. So what do I mean by this? Let me give you an example of Painlevé equation that will be relevant later in order to understand what is this guy here. So example. Of course I cannot list all the 6 Painlevé equations because they are very long, but I want to just write 2 of them. The first one is at least on the affine line is polynomial. So W7 equal to 6 W squared plus T. And the other that I want to write on the blackboard is the third one. W7 second equals to w third over w minus w prime over t plus alpha plus beta. Maybe there is some minus somewhere, but I don't think we will complain of it. Is w cube plus delta. So, where all these parameters are complex numbers, so with alpha, so I wrote this for two reasons, because first I will, without much details, because the computations are long, but I will construct the space of initial condition for P1. And the reason why I showed you P3, because it is a very special among all the Painlevé equation for many reasons. For instance, just look at for some special value of the parameters here, you find a specific equation which has a specific solution. So there will be three different versions of this P3. You will see in a second in the classification when I will give the classification. Okay, so for instance, we have that in this case, tau is the whole affine line, while in this case, tau is the affine line minus 0 and minus 0. Okay? So let me write explicitly what's the space of initial conditions for the others. So we have.
And this tau has nothing to do with tau functions.
Sorry?
And this tau has nothing to do with tau functions.
Which tau? No, this is time.
No, tau.
Ah, no, tau is capital tau. No, has nothing to do. It's a domain inside, just a domain. Yeah. It's the complex line minus referently many points. Yes, nothing to do. There will be at some point some elliptic functions, so there will be something, but not exactly in that direction. So we have that. So fact, just to let you know what are the points. Tau 1 equals to tau 2 equals to tau 4 equals to c. So for in this case is always the complex line, while we have that tau 3 equals to tau 5 equals to complex line minus 0. And for 3 you see here, and while the last one is special, so tau 6 is c minus 0 and 1. Of course, these are models, okay? It's not just every time. So,
sorry, but this is second order, so why you specify only one? If you specify initial conditions for a second order equation, then you need also the first derivative, no?
Yes, indeed, in a second I'm going to consider an Hamiltonian system, so what's the problem? No, this is not, sorry, no, these are just the fixed singularity of t. This is C is for t.
So this is space of time.
Yes, it's only for t. I want to
discard
discard
for t.
It's not for, no, it's not for w. It's not for,
this
it's
is
for
for
t.
time,
It's
not
not
for
for.
w.
It's,
Okay.
The space of initial condition is not yet there. There will be a vibration over this tau, and the fibers will be the spaces of initial conditions.
Okay. So you are parameterizing where you can put the initial condition.
Exactly.
And then you will specify what are the
I don't want to put initial condition over t equal to 0. Exactly.
Yeah.
Yes.
Okay.
This is the point. Yeah, thank you. Any other question? Yes, the space of initial condition takes time to be defined. So in a second we will be there, but
Okay.
So tau again is what is its domain, but for the function branches we are solving equation.
for the moment it's nothing. It's just a fine line minus fixed singularities.
Okay.
Over the I will construct a vibration over tau. And the fibers will be the spaces of initial condition, so the spaces for which you choose. But the first thing that you would like to do, because I have to translate from this version to the Hamiltonian one, and I will not say nothing but what is the Hamiltonian form. So fact, because otherwise it's going to be 3 hours, but just to say that fact, to every equation, one can associate an equivalent first order system of this form. Let me copy, but it's what you imagine. So I will need also a label for this, which is Q prime equal to sorry, P, and P prime equal to H. So you can always convert your Painlevé equation in
There
the
should be sign.
Huh?
There should be sign in one of these equations.
Ah, yes, you're right. Where?
Anywhere.
Okay.
You can choose.
So where H is, so where H is regular on C2 times tau. So let me say that also this H is an H bullet. So to every Painlevé equation, which is a second order differential equation in one variable, you can associate a first order linear system of differential equation in two variables. And this is the starting point, because what we actually want is, as Alessandro was pointed out, two initial conditions, which here are one for W and the other for W prime. In this alternative and equivalent version, it's just something for P and something for Q. The other thing that I want to say about these two systems is what is the how the Painlevé property reflects on these systems, and you can see this on continuing solution along path. So let me write it. So remark Painlevé property, since around every movable singularity solutions are single valued, we have that Painlevé property implies that every solution at P equal to P star can be meromorphically extended to any dot tau bullet starting from tau T star. So we understood why so. I think I explained this. Now the point is that, of course, you don't like it because you want solutions to be extended holomorphically and not meromorphically, but the presence of movable singularities is still there. So you want to somehow get rid of this fact that they can be meromorphic, sorry, extended continuity, sorry, extended is not. So what we want to do is to find a suitable space which replaces this C2 with the property that all solutions can be continued holomorphically, so analytically. The problem is that a suitable space is going to be a compactification of C2, but not all compactifications we like, because there might be some other issue that I'm going to explain in a second. So we want to get rid of this holomorphically, meromorphically. So we need to compactify suitable C. Okay? And I want to explain what do I mean by this. So, property A, we want that every solution can be continued analytically. when I write this, I mean all these sentences that I don't want to write all the time. But we don't want so we want unicity. We want so we don't want points through which all the solution, infinitely many solutions passes. So we want to get rid of this. And so what you do is in general, but I will explain this more carefully, but in general, you consider some compactification such that A holds, and then you perform a series of blow up and blow down. Then so again to get it. So one might, I will explain, but for people that already have in mind that it is enough to blow up, it is not enough to blow up. Sometimes you really need to contract some curve. Suppose that your compactification are one curve which is not expected to be there. What do I mean is not expected to be there? The flow is saying, say that you have one integral curve, which is at every point is a curve, but because of the blow up you have a line at some point. Okay? This line must be contracted. But if you, since the surface you are looking for is smooth, you cannot see singularities which lives along a curve because of the discriminant theorem, because of the fact that on a smooth surface by rational map are not defined over points and not over line. So you really need to blow down. I will show examples. It's just to explain that it's not enough, as for resolution of singularities, it's not enough just to blow up, but you might need also to blow down. Okay, any question? Yes?
Could you read the word in condition B after want?
Unicity
Okay.
of the solutions. So blow up, I mean, I explained a bit last time and I will show some picture today. But the blow up, the idea of the blow up is that, roughly speaking, on a surface, a blow up separates all the transverse curve passing through the point you are blowing up. So the solutions passing through the same point are these transversal curves, and the blow up is the operation that separates them. But there might be some exceeding curve that you have to get rid of. Okay, great. So, I want to draw some pictures just to give an idea of all the process, because we already built the space of stability condition in some sense. So I will draw a picture of the steps, then I give the definition of space of stability condition, and then I explain.
Stability conditions or initial?
Initial conditions.
Initial, not stability.
Ah, set stability, sorry.
I understand why, but
Yeah, sorry, because stability conditions is another project, so the initial conditions, yes. Yes. And then I will give an example to explain how the relation with, so which kind of tools from algebraic geometry you can use developing this theory. So, what you do is you start with your copy of C2 cross tau star, so you can imagine it's something like this. It's a plane with some missed line here at infinity. And as we saw, the problem, the initial problem A that we want to solve is that some solution might escape might try to go to infinity. Okay? So this is the first thing we want to solve. And maybe we solve this by compactifying somehow, doesn't matter how. So we get a new picture, and now somewhere we see infinitely many, I can draw this, infinitely many solutions passing to a point. So this is the other problem that we want to solve. And so we blow up this point, which means just we remove the point of intersection and we replace it with a projective line. Okay? So that we separate all the lines passing through here. So now all the lines are separated while the yellow point here corresponds to this yellow line here. And now we still have a problem because it is true that not all the solutions, there are not infinitely many solutions passing through a point, but we don't have unicity here because actually this yellow line happens to be a leaf, so a solution of union of integral types of the foliation. I'm going to explain, so of the differential equation, sorry. And so what we do as a last step, so let me call this S, so here we have S times tau. As a last step we remove the yellow leaves, the yellow line. And again we are not compact, but we are happy of this situation and I'm going to explain why. Okay? And I'll call this and I will call this E times yes. So probably the whole thing here I call E. And of course E has a projection over tau. Let me write everything with good. So the point is that in a second I'm going to give the definition, but our space of initial condition will be E. So and more specifically the triangle. Okay? But I need to say what is a space of initial conditions. And we will get information from the geometry of S. So S is a projective surface. On a projective surface we can do intersection theory, we can study cohomology, we can study a lot of things. And so strictly speaking E will be the space of initial conditions, but the geometry of that compactification is what we care about. So this of the fiber of that one is there, the projection there. Now I have a very, very long definition, so keep calm and wait that I write it. It should be the longest. There. Okay, where it is? Here. So definition. Yeah, so let a bullet be a cycle. Such that first, a bullet is a quasi projective variety containing an open dense subset tau isomorphic to C2 times tau star. So what is this tau isomorphic? Means just that we have a bullet over tau star, this C2 times tau star, which is open subset, and we require, so we also have a projection and we require this diagram to commute. Okay? Then we say that the flow of triangle defines smooth transversal, sorry, a smooth uniform foliation. Okay, in one-dimensional complex leaves transversal to pi if it's a very long definition. For every f leaf of so in particular the name f the smooth foliation f. So f is a foliation, so it decomposes the E as a disjoint union of one-dimensional leaves, and what I require is that every leaf of f intersect transversally every 5. So for every leaf of f and for every t in tau bullet, f intersect transversally t, the fiber over t at a point, just one point. And second, for every path inside tau star can be lifted to any to the leaf passing to any point whereas maybe starting in T. Okay, so this very let me say, but this is precisely what we said before. But let me say this explicitly. So we say that the foliation defined by the flow of the differential equation is made of leaves which are transverse to the map if every intersection between a leaf and a fiber is 1 point, is transverse and it is 1 point, and we can lift every path from tau star to the space above. And this will be the way in which we will build the solution in the space of initial condition. In particular, if so, the tripole is a space of initial condition for the Painlevé corresponding Painlevé equation. So why? Because now we can lift any path, and every solution can be uniquely continued analytically. Every point admits a unique solution. Around every point there exists a unique solution of the equation. So in this sense, this tripole is a space of initial conditions, meaning that if you take a point of E as initial conditions for your equations, then every solution can be analytically continued along any path from below. Okay. The problem in general, even if we are doing algebraic geometry, this is not a suitable object for an algebraic geometer, because the remark here is that even if E carries a structure of fiber bundle and it is quasi-projective, This fiber bundle is not algebraic. Why so? Because the trivialization is given by the flow of the Painlevé equation, which is not algebraic in general. So the trivialization of this fiber bundle in general is not, the transition functions in general are not algebraic functions. So this is because the trivialization is given by the flow. So algebraic geometers don't want to work with E, but they actually want to work with one fiber of the map to tau. But better, they want to work, so we want to work with the compactification S. Okay? And in a second, it will be clear why we like S, because it has a lot, again, of homological information coming from intersection theory and so on that are very useful to classify the equation. So very briefly, I want to say a couple of things and then give the example. So now I can probably. So okay. A fact now, because I cannot give the proof, but I can draw a picture that explains you how it works, is that if we look at S, so now focus on S, and we have that S minus T. So I take a fiber, so I can remove this open subset from S, is the support of an anti-canonical divisor, an effective anti-canonical divisor, and its dual graph is of extended infinite. So in a second I will write the table. So the point is that this it works similarly to Mackay correspondence. We have a bunch of -2 curves. I will also say I didn't write this at the blackboard, but we have a bunch of -2 curves. They intersect, so the dual graph of a collection of curves is just the intersection graph, and they intersect according to a thinking diagram. I will draw a picture now, partially now or partially later. I will draw a picture in any case, but just let me, now I can list all the possibilities. So P1 corresponds to E81, P2 correspond to E7, 1. This 1 means extended. So if you know what is E8 or E7, the extended is just you add one node corresponding to something. I don't want to enter in the details, but it is in many areas of mathematics. P3 is D8 or D7 or D6. And now you see we have 3 cases because there are the limit cases that I mentioned at you at the beginning. This is just for P3. And then we have P4, which is P6. And P5 is P5. And P6 is D4. So, when you have a differential equation of the kind treated by Gambier and Painlevé, what you do is you build a space of initial condition which is not hard, might be long but it's not hard, and once you look at the geometry of an effective anti-canonical divisor, you realize immediately by the intersection of its irreducible component, you realize immediately that in which case you are, to which Painlevé equation your equation is equivalent. So the example here is the following. If you start, so the example, if you consider P1, and you start from C2 times tau, and the first time you compactify, you get a P2, so this is a toric description of P2. And you see that you have to blow up one point, which is T infinity, no? If you want. Sorry, no, not T infinity, pardon. You have to blow up one point, because if you see the equation, you have to blow up one point. No, let me explain why, because yes, it is infinity, but in the affine line, so it's not in T infinity. You have to blow up one point, so what happens is that you get a P. The first thing is the surface here, where you have an exceptional line E1, okay? And with abuse-of notation, if this is an hyperplane H, I will use the same letter here for the hyperplane, for the pullback, so the strict transform is just H minus E1. So here I'm implicitly writing the pullback, because I don't have names for all the maps. Then you see that you have to blow up this point. And with the same argument, here you have E2, and here E1 minus E2. Remember, this E1 is not the same as this is the pullback. E2, and here you have H minus E1 minus E2. Then you keep going, I don't want to, so you keep going, and the last one is the following. Okay, and so here you still have E1 minus E2, and here H minus E1 minus E2 minus E3. And you do the computation, and you see that the vertical leaf, so the curves that you have to remove are this one. So I took the colors for this. So these are the curves you have to remove. And so why I'm writing all of this? Because now I want to show you that actually the anti-canonical divisor, that there is an effective anti-canonical divisor which is supported over these curves. So this is just a sequence of blocks. You do the computation and you lift the differential equation. Not that. But I will also show you the blow-up in a second, but what I want to say is that, so if I take all these all these irreducible curves, so let me give them names. You call D0 equal to E8 minus E9. So E9 is the last one, and so the previous one is E8 minus E9. Then you have DI equal to I minus E. I plus 1 for I from 1 to 7, and then you have the rate is H minus 1 minus 2 minus 3. And you see that if you consider this divisor, D, which is D0 plus 2D1 plus 4D2 plus 6D3 plus 5D4 plus 4D5 plus 3D6 plus 2D7 plus 3D8. This is equal to 3H minus sum of the EI. And now, so this is very easy to find. It's just linear algebra, because you do a computation inside the Picard group of a surface that you know, because it's built as a blow-up of P2 points that you know. And so what you get at the end is this number, which by a junction formula, this is precisely an element of the anti-canonical linear system, an effective element of the anti-canonical linear system. So as you can see, the support of this effective divisor is precisely the union of the cards coming from the construction by Okamoto. And once you have all this data, you also can show that every di, the remark that d I square equal to -2 for every I. Okay. So in one word, I would like to say what happens to the differential equation when you perform this construction. So what do you see when you do the I mean, I will not do the computation at the blackboard, but what is the prototypical computation that you have to do? So what do you I mean, how this behaves? So an example is that if you start from P1 defined, or better is definitely the first Painlevé equation defined of P2. So remember that it has some singularity at the line at infinity, which is this H here by choice, it's just a choice. You can find the equivalent description. So example, in a coordinate chart U2 should be automorphic to with coordinate W, P. So I'm not choosing P and Q. P and Q are the coordinates in the chart U0, so these are the coordinates in some other coordinate chart. Every solution of P1 has the form so this is an expansion of the solution. Where A and B are some function which have higher order, which vanish at t equal to star with higher order. And this is just to show you that at every solution passes through the point 0, 0 at t star equal to 0. So this is the point that we want kind of split using the blow-up. So let's see how the blow-up affects this point. So we just look at one chart, we know that how to write the blow-up. If you don't know, there are the notes that I've written for when I gave this course in Iran. But blow-up is just the following thing locally. So locally, we take a copy of C2 with coordinates, so I don't want to choose the coordinates by heart, so you take a copy of C2 with coordinates U and V, and you go to C2 with coordinates W and Z, and you send the point UV to the point UV. In particular, W equals to UV, sorry, no W, U equals to W over Z. No? UV equal W, V equal Z, so U equal W over Z. So in these new coordinates, U and V, which are coordinates on the blow-up, the first entry of the map has a vanishing of lower order in the first entry, no? Because if you do first entry over the second entry, the order of vanishing at t equal to t star is one less. So what you do is you keep continuing blowing up until there are no infinitely many solutions passing through a point. Okay? So this is the typical example of computation you have to do. So in the last 10 minutes, I would like to say something about the continuous case. So the discrete case, yes. So the point, the idea of Sakai, so for a long time, because this theory is from 2001, for a long time, people tried to understand what should be the analog, the discrete analog of Painlevé equations. And the idea of Sakai is to not start from a difference equation, but to start from a surface, and then to show that using the symmetries of the surface, you can define some difference equation defining suitable sequences. For instance, sequences which have zero algebraic entropy, as we were talking last time. So the construction goes like this. So first you say that a generalized Alfen surface is S is a projective surface such that there exists an effective anticanonical divisor, which is a combination of primes with Ks times Pi equals 0 for all I. And this in particular fact, generalized Alfen implies that the dimension of this anticanonical is 0 or 1. So these are not the surfaces we care about, but actually we want a surface having this number equal to 0, so the definition is that a generalized Alfen surface is Sakai if the dimension of the anticanonical series is 0. It's just one point. In other words, we want that there is just one effective anticanonical divisor. But this is precisely the kind of surface we have just seen, no? The previous surface I didn't say, we blown up P2 at 9 points, and this is precisely the prototypical object. So let me explain with a picture. So you know that on P2, the anticanonical is given by cubics. So minus is given by cubics. And on P2. So by adjunction, by blow-up formula, we know that on S, which is a blow-up of P2, minus Ks is given by is the pullback of Kp2 minus Kp2 plus minus the sum of the exceptional divisors. So you see that you don't want this minus because you want this to be effective, and so the only way you have to have this effective is that something here cancels with something here. So if we consider a cubic passing through 9 points, and the 9 points are in general position, then we have precisely a unique cubic passing through those points, because this is isomorphic to P9. So what you actually do is you take a cubic and take another cubic. Then you take 8 of the 9 intersection points. And since we know that any other cubic passing through these 8 points also passes to the 9th, if we take as a 9 point a point not lying, so lying in one cubic but not in the other, this cubic is the unique cubic passing to the 9 points. And so on the blow up of these 9 points, this is the unique effective anticanonical divisor. And so I build a Sakai surface. But now, as you can see, you can consider phi to be an automorphism coming from some phi tilde, which is a birational morphism of P2. In other words, it's just something that or is not defined on the point, on the base points, or just permute them. Then, the difference equation of the following, where x is a point of P2, this is a Painlevé difference equation. So, Painlevé difference equations are not defined by some property of being regular or whatever you want, but just starting from the continuous one, you build the analog, the analog surfaces, and then you say, and then you declare that difference equations coming from the automorphism of the surface are Painlevé difference equations. Why is so rich the theory here? I don't have time to explain, but the point is that inside here you have all the theory of weight groups to develop, and so you have different many kind of automorphism giving rise to three different kind of difference equations, and this theory is very rich and is quite settled in dimension 2 because the classification of Sakai surfaces was given by Sakai. But in dimension 3 this is not settled at all, and indeed I would like to finish with a picture to explain what's the difficulty in dimension 3. So, this is kind of standard now, and what people are trying to do is to develop the analog theory in higher dimension. And it's not something expected to be developed at once in all higher dimension. Already doing just in dimension 3 is a big deal because of what I'm going to explain now. So there is something called the mean-chain theorem, the mean-chain system, which is a system in 3 dimensions, which restricts as Painlevé 6 on subsurfaces. I don't want to talk about this. I just want to show you what happens when we look at some compactification to the indeterminacies. So I told you that it is a system on C3. So I can consider, for instance, 2 different compactifications, P1 cross P1 cross P1 or P3. So let me draw a picture of what happens. So I represent P1 cross P1 cross P1 as a cube. So for instance, here you have the point 0, 0, 0, and here you have the point infinity, infinity, infinity. So you can figure out the rest of the picture, while I can represent the P3. So this is P1 cube. P3 I can represent this way. So how are my indeterminacy located in this space? No? Because then I want to find this is, for instance, in the continuous setting. So already I can talk about Painlevé, here I can talk about Painlevé property. And so how can I build a space of initial condition? I look in determinacies and I try to go up. But the indeterminacies are so located. So I have 2 indeterminacies here, 2 lines of indeterminacies. One is here. One is here. And then I have a cusp here. And another. So this is what happens on P1 cross P1 cross P1. While on the other side, this is what's going on. So these are the singularities. So differently from the 2-dimensional case, or differently from the case that I showed you last time, now we have 1-dimensional, so positive dimensional singularities, and they meet at some point. The problem here is now that 2 things. First, when you blow up something, then the equation somehow changes when you pull back the equation. And something that was of degree 1 might have some higher degree if is meeting the object you are drawing up. So stuff that here are linear maybe are not linear when you build the block, so computing the stuff is much harder. But the actual problem is that while if you have distinct points, there is no difference between in the order in which you go up them. Here the order make to explain you that the order is important, I draw on the blackboard a possible choice. So last time I explained to you what happens when you blow up 3 concurrent lines. And now I want to say just what happened with 2 lines, just to show how hard it is to decide how to proceed. So this is really the last thing I want to say, which is the following. Suppose that you start with 2 lines in the affine tree space, line M and line N, okay? And so, for instance, 2 lines meeting at a point, you see here there is an example, here there is another example, here there is another example. There are also worst examples where 3 lines pass through a point, but let me explain at least what happens when I have 1 point. So, I can choose, I want to start to blow up them, and I have many choices, because I can, for instance, first blow up this line, and I get something like this. And then I blow up this line, and I get something like this. I will need to get the blackboard then. So this is a sequence of both. But then I might also blow up differently. I can first blow up the first, and then blow up the second. Or I can choose differently. I can, since the blow up involves the set of equations, I can use the intersection of the set of equations of the product of the set of the equation. The two define the same locus. So if I look at the intersection of the defining equation, I get something like this in the middle. So this is given by blowing up the intersection ideal of L. There's an ideal of L and the ideal of M. And you have a conical point here. And notice that these two are the 2 small resolutions of the conical point. So there is a plot between the 2. But now, once you are here, you have a common resolution, so the big resolution. You have the 2 small resolutions, so you have the big resolution of these conical points. That is going to be something like this. But you can also do differently. So you might start, for instance, so I need more space. So you can also do differently, as I told you. Instead of using as defining equation the intersection of the 2 defining equations, you can look at the product of all the possible defining equations. And so you get a different option. So everything there is computable. I'm giving you the answer directly, but you get something like this with a conical point here. Notice that this guy here is a small resolution of this conical point. So you have another map from here to here. The other thing that you can do is to blow up first the origin, and then the 2 lines. But now again, this is a small resolution of this guy here, because instead of inflating a P1 vertically, we did it horizontally. And so we have a flop here as well. And finally, to conclude, the 2 have in common a resolution, which is the big one. So at any intersection point in the picture that I just erased, you have all these choices. So it's not easy to understand if you build a space of initial conditions or not. Even because you cannot, I mean, this blow up is local, but if the 2 stuff meet, there is a point that every neighborhood of that point see both the complete component of the indeterminacy locus. So yes, it's not clear. Thank you.
first, so in this high-dimensional situation, so if we look from the Hamiltonian perspective, we would rather consider even-dimensional cases, dimension 2, dimension 4, and so on. So in this case, this three-dimensional picture is
Actually, no. Actually, this is already the replacement for the Hamiltonian before. So it is already dimension 3. We are not going to consider an Hamiltonian form for this equation. We have already the equation in the form x prime equal to rational combination of y prime, z prime. So we never thought to look at the Hamiltonian version. No, never tried.
I mean, in this case,
Yes.
no hope, but
Yes.
in this three-dimensional. So last time you stated some theorem in this three-dimensional case.
What's discrete? This is continuous.
Do you have any theorem in continuous three-dimensional case?
No, that's the point. That's the point. What we know is that the system that we looked at has something called the double surface, which is a surface which is let's say equivariant with respect to the action of with respect to the flow of the system. And if you restrict your system to the surface is highly singular, but then you can build a resolution of the singularities and a birational model such that the system restricted to the surface is P6. And since this system has also a lot of integrable autonomous limit that I didn't mention, we have a strong expectation that we have integrability as well for the system itself. But we don't understand, because to understand it you might work in many ways. So you have to do or an analytic local study or a geometrical approach. So these are the difficulties for the geometrical approach. I actually don't know the difficulties for the analytic from the analytic viewpoint, but I can expect that are harder than this one, because at least here you have a finitely many possibility, and then you can play with them. Yeah.
These extended Lincoln diagrams also show up in like as exceptional fibers for elliptic fibrations.
Yes, indeed. Thank you for the question. The point is that there were is there? Yes. In the case in which you have 1 here, is precisely the case in which you take the 9 points which are the intersection of two cubics. And this defines for you, this also gives you the discrete discrete system, which is often integrable, but the surface that you obtain then is elliptic, because all the pencil of elliptic curves passing through these 9 points gives you an effective anticanonical divisor, and this is your elliptic fibration. And a certain number of fiber will be singular, and the nice thing is that also the singular fiber are enough to understand the behavior of of this sequence here. For instance, if you look at the so-called Q P1, which is a discrete version of the P1 that I presented at the beginning, what you get is that the two have the same space of initial condition, which had this intersection graph, and then 5 these. In total, 9 nodes, yes. And in this case, you have a Sakai surface. But if you look at this other one, xy goes in y, xy minus 1 to x minus 2. Your point lie on a singular. The point that you will consider lie on a singular fiber. Let me explain the picture. Let me draw it and then I explain. So this is a pictorial description of P1 cross P1. So this is a P1, this is a P1, and this is a bilinear. This is a bilinear curve. So something coming from a conic, and so we have something coming from a not coordinate line. So the degree of this guy is 3, but this is a singular fiber of the elliptic fibration. Okay? Because of this. And also you have another meeting point at infinity. Okay? So in this case, you don't have a Sakai surface. You have this is not a Painlevé difference equation, for instance. But still, you can study it. You can study the symmetries of these points, giving you some iteration. So this is for the discrete case. So, but for the Sakai surface, you don't have the elliptic vibration because of this. At least it's not the anti-canonical. Maybe you have something else, but I don't think so. I think that it's always the block of P2 at 9 points chosen in that way. So probably knows, but I don't think there are different vibration possible other than the